Welcome to Centrifugal Governors, and this is Circular Motion Part 2. In the previous topic, we talked about Circular Motion Part 1, where we just discussed the general principles. So this time, we apply them on a centrifugal governor, as you can see in that picture. That's a typical centrifugal governor, which has been in use for many years, and that's a model that was used in the past. So a centrifugal governor is simply, or rather a governor generally, a device that we use to measure or regulate the mean speed of an engine. Meaning that even if you may go through different terrains where maybe you're going uphill, there's a load, we want the speed of that engine to be maintained constant. So how do you do that? It's by use of this mechanism, which is a centrifugal governor. The way it's going to do that is when it is rotating, these masses will fly out, thereby causing this to rise. And a link is attached there, which will facilitate in the opening or closing of the throttle so that more fuel can go in. And you end up with a rich or lean mixture so that you have a power that is coming out of there, helping us to maintain the engine speed constant. And it will be maintained within specified limits. Now, are there some types? We may have quite a number, but the two broad families that have been used so far in the past, we have these centrifugal governors that use a deadweight and others that use a spring or they're spring loaded. So when you talk about the deadweight family, that's where we find the Porter governor, the one shown in the picture here, which has the mass at the center, and the other one, which is the Watt governor. Of course, the name centrifugal comes from the fact that we use the centrifugal force to ensure that we can arrive at what we want to achieve, which is the closing and opening of the throttle, thereby controlling the engine speed. Here is your Watt governor. In a Watt governor, you have a very simple arrangement. There are just these links of uniform length, and between them are these two masses. There's nothing at the center here. This is the fixed sleeve. Some of them can have a nut, and then this is a movable sleeve which is able to move there. When it comes up, it means these balls will move out. The only reason that will cause it to move up is when the speed is very high. So you have this movement like that along that guide. Then in the end, we are controlling the opening, partial or full opening of the throttle. Now, to find the mean engine speed, we take moments about that point, which is B. Here we just have two forces, this and the other one there. So this one is the weight, which is a product of mass and acceleration due to gravity. The product, that force there, you multiply by this perpendicular distance. This one gives you a clockwise moment. So mv squared over r times the distance coming down here. Now we don't have anything here, which compels us to make use of this distance from here up to there, because AC is the same as the distance that we have from there up to this point. And that's why we have this here, mv squared over r times AC. Then the other one is just mg multiplied by this perpendicular distance. So we have this expression there. When you simplify, you can see there's m here and m there. Then that's what you have. You can make V the subject of the formula. And when you make V the subject, you multiply both sides by R, which gives you the top part there. You also divide by this AC on both sides so that here it cancels, but on the other side you have that. Because V is carrying a square, it means we introduce the root sign, thereby get rid of that square. So that's the final expression for the mean engine speed when you are dealing with a Watt governor. Something similar, when you're dealing with a Porter governor, we have a central mass there. But it has an advantage because you are able to now handle higher speeds and even increase loads. So with this central mass, it means it has to be divided between the two because it's at the center and we're analyzing on the one side of it. So taking moments about here, you have mv squared over r times that. Meaning mv squared over r times AC like we saw earlier. Just like we had in the area one where mg times cb, which is this times that, then we add this one, which is m1g over 2 times that distance, which is d up to b. This is the line of action of m1g. We are calling it m1 so that we can differentiate it from the mass between each of those pairs of arms. This is m1. And so you have m1g over 2 times db. That gives us the general expression for a Porter governor. Look at this example. You have a governor which has uniform arms of length 100 millimeters, and then the angle between this pair of arms and the vertical, rather between each arm and the vertical, is 25 degrees. Determine the mean speed which can be accommodated by this governor. So we have 25 degrees as the angle. Now with that angle, it means we can now make this the subject. So we go back to sine, which is CB over AB. Then this CB is equal to that because sine is normally opposite over that. How does that make sense? Because this is CB, which is opposite that angle, which is the arm and the vertical, this angle, and this is the hypotenuse. So CB over AB gives us sine of an angle. And that's how come we have this. Then making CB the subject, AB times sine, that we substitute. Then the other thing you can notice is that this same CB is actually the radius. It's the same as DC. It's the radius. So that's how come it's written like this. R is equal to CB, which is equal to 0.8452. When it comes to AC, AC is the adjacent side. This one was the opposite side. So we just substitute where there was sine, we put cos. And the rest of the substitution, we put 0.2 there. This is our answer. So once we have these, and this is where you need to be very careful not to make mistakes because mistakes can easily be made here. So then V is equal to this, which is the acceleration due to gravity, R times that. This is the standard formula, or the formula that we derived earlier, which you can easily come up with when you just resolve like we did. So G is here, 9.81. Multiply that by this R. And R and CB are the same, so that's why there's this repeat here. Divide by AC, and that's our AC. When you compute this in your calculator, and then get to the square root, that's what you find. So that is our mean engine speed for this governor. Great, now let's get to the second example. The example number 2. So in this case, we have a Porter governor which has uniform arms of length 250 millimeters each with a mass of 900 grams attached between each of those pairs. The angle between each arm and the horizontal axis is 30 degrees. If the engine mean speed is 300 RPM, determine the magnitude of the central mass. So one thing you will notice is that this is a repeat of the earlier calculation we went through where we say BC is AB sine theta. The only trick is this here. it says the angle between the horizontal axis and each arm is 30 degrees. It is now referring to this, meaning that this angle here is 30 degrees. So to get the other angle up there, we'll just subtract this from 90, and 90 minus 30 is 60. So that's how come we're using 60 here, there, AB sine 60. And of course, since AB is 0.25, we just substitute. And once we compute this, we get this one here, 0.2165. Then V is omega R. Omega, W is 2 pi n over 60. R is this one we just found here. So 2 pi times 300 over 60 multiplied by that, that's the answer we find. AC, where they will sign, we just put cos. It will be AB cos 60. And that's 0.25 cos 60, which gives us that expression. The answer there is 0.125. And finally, BD is twice CB. How? From point B to point D, you multiply this by 2 because this is the radius. It's like you're asking for the diameter when you've been given the radius. Just multiply the radius by 2 and you are done. So for that reason, we have 2CB. We have BD being equal to 2CB. And that's how come we multiply now 2 by that. CB is the same as CD. So there you go. The answer now is 0.433. With all this, we now need to make use of this expression we derived here after resolving that one. So there we have mb squared over r times AC, which is the centrifugal force giving us the clockwise moment, equals this expression here. This is m1 and this is m, very different ones. So we just substitute. Mass is 0.9. Our V is this. And we are multiplying. Already we are saying this is squared. Then we are multiplying by AC, which is this number here. Everything divided by R. And there we have it there. Then mass again, 0.9 times G 9.81 times this one. This is the same as the radius like we saw earlier. Then plus M1, which we're looking for. Then there's G times dB, or simply BD. That's 0.433 over 2. Then the answer we find is that number there, 10.42 kg. You may notice that the speed slightly goes up because of the way, just the way the numbers have been distributed, and even the kind of speed we may be having there. Otherwise, this is the correct answer following that procedure. So this is the second application of circular motion. From here, we have a small exercise that should give you a chance to try out what we've just discussed with 3 questions, and feel free to solve each of them. Where you have a problem, I'm very reachable. You can always ask and put a comment below there or get in touch with me. Thank you very much for paying attention.